All right, welcome. In this explainer, we're really going to level up your C programming skills. We're going to go from the basics of repetition all the way up to some super powerful concepts about how C actually handles memory.
Okay, so here's our roadmap for today. We're going to kick things off with the building blocks, nested loops. And then we'll build our way up to the really fascinating stuff, like how functions work with data under the hood.
All right, first up, nested loops. We're going to master the art of putting loops inside of other loops. It's an absolutely fundamental concept for building, more complex and interesting programs. Okay, so before we can even think about nesting loops, we've got to make sure we're totally solid on how a basic while loop works all by itself. It's really just a simple way to get repetition. So the goal of this little piece of code we're about to write, just print the word hi 5 times. That's it.
So have a look at this. The logic is super straightforward. We create a variable, I, and start it at 0. And then the rule is, as long as I is less than 5, the loop is going to print hi, and then, and this is key, it adds 1 to I. It's just a simple, totally predictable counter. And when we run it, what do we get? Exactly what we'd expect. 5 lines of hi. See? The loop did its job 5 times, and then it stopped. Okay, so that was the easy part. Now, let's see what happens when we get a little more adventurous and stick a second while loop right inside the first one. So in this new version, you'll see we brought in a second variable. We'll call it j. And this j belongs to a second while loop that's living completely inside our original one. This new inner loop, it's got its own counter and its own rules.
Now, this is the most important part to get. That inner loop, the one controlled by j, it's going to run to completion for every single time the outer loop runs. So for each one time I ticks up, j is going to do its entire cycle from 0 all the way to 2.
And check out the result when we run it. We get 5 lines, right? And each line has 2, 2, 2. That is the nested loop in action. The outer loop made the 5 rows, and that little inner loop, well, it was responsible for putting 3 2s on each of those rows.
So let's break down exactly what the compiler is thinking here. First, the outer loop checks I. If the condition is true, it jumps inside. Now, the very first thing it does is reset our inner counter j back to 0. This is so important. Then, and only then, does the inner loop run completely, printing 2, 2 3 times. Once that's all done, the program prints a new line, bumps I up by 1, and then it goes all the way back to the top to start the whole process over again. Okay, now for a super important warning. If you forget to increment your inner loop variable, that j++, what happens? Well, j will never reach its exit condition. It'll just stay at 0, forever. And your program? It's going to get stuck in an infinite loop, just printing 2 over and over and over again. So please, always double-check your incrementers. So why are we even bothering with all this? Well, nested loops are literally the key to working with two-dimensional data. Just think of it like this. The outer loop controls the rows of a grid, and the inner loop, it controls the columns inside each of those rows. This is fundamental for everything from printing out tables to processing the pixels on your screen. All right, so now that we're pros at repeating code, let's figure out how to package it up into these neat, reusable blocks called functions, or as I like to call them, little magic boxes. You know, every function really has 3 main parts. The first one is called the prototype. Think of this as a promise you make to the compiler. You're basically saying, hey, trust me, I'm going to define this function later. It spells out the function's name, what kind of data it gives back, and what kinds of data it takes in. And this little promise, it usually lives in a header file. So for example, something like int add numbers int a, int b, that's a simple one-line promise. It tells the compiler everything it needs to know up front. There's a function coming that takes 2 integers, and when it's done, it will give back an integer. Okay, part 2 is the definition. This is the real deal. This is the actual code, the set of instructions inside our magic box that does all the heavy lifting. This is where all the logic lives. So to follow through on our promise, the definition for add numbers contains all the logic. It declares a temporary variable called sum, it does the math, and then it uses that special return keyword to send the final result back out. And the third piece of the puzzle? Local variables. That sum variable we just made, that's a perfect example of a local variable. I want you to think of these like toys that can only be played with inside this specific function's box. The second the function is done and it returns, poof,
that sum variable is gone. It completely vanishes. That's why they're called automatic variables. They're created when you enter the function and destroyed the moment you leave.
And finally, to actually use our magic box, all we have to do is call it from our main program. So we can create a variable, maybe result, and then we just assign it the value that comes back from our function call, like this. Result equals, add numbers, 10, 20. Yep, it's really that easy. Okay, next up, let's talk about a special kind of function, the kind that doesn't actually give you anything back. And while we're at it, I'll show you how C functions are surprisingly similar to something you might have already played with. You know, sometimes a function's only job is to just do something, right? Like print a message to the screen. It's not supposed to calculate an answer and give it back. For those cases, we use a special keyword, void. When you see void as the return type, it literally means this function returns, well, nothing. Take a look at this say hello function. Its only goal is to print a message. And notice something important. There's no return statement at all. It doesn't need one. It just does its thing and then it's done. Void isn't just for return types, you can also use it for parameters. So if a function doesn't take any inputs at all, you just specify void in the parentheses. And I bet you've seen this 100 times already in int main void. It's just a crystal clear signal to the compiler and to anyone else reading your code that this function doesn't need any arguments to do its job. So really, void is just a super clear signal for nothing. It's either telling you there's no input or no output. So a void function void, that's just a totally self-contained action. An int function void creates a value out of thin air. And a void function int x, well, that takes in a value, does something with it, but doesn't bother reporting back with a result. Okay, so this all leads to a really common problem, especially as your programs start to get bigger. What do you think happens if you try to use one of your magic boxes, call a function in main, before you've told the compiler that it even exists? Yep, you get an error. You see, the compiler reads your code from top to bottom, and if it bumps into a function call it's never been introduced to, it just gets totally confused and gives up. The fix for this is something called a forward declaration. And all that is just taking that function's prototype, that promise, and sticking it at the top of your file before the function ever gets called. As you can see here, by just adding void, do something void right at the top, we make the compiler aware of our promise ahead of time, and the code compiles perfectly.
And you know what? This whole idea connects directly to another tool you might have used. If you've ever played around with Scratch, defining a function in C is the exact same idea as using the make a block feature. I mean, think about it. In both cases, you're just bundling up a set of instructions, slapping a name on it, and creating a brand new reusable command.
So we've seen functions call other functions, that's pretty normal. But what if a function calls itself? This is a really powerful and sometimes kind of mind-bending concept called recursion. Let's dive into a classic example to see how it works. Calculating a factorial. Where 5 factorial is 5 times 4 times 3 times 2 times 1. This is a perfect problem for recursion, because to figure out the factorial of 5, you first need to know the factorial of 4, and so on down the line. Now, in this function, the very first thing we do is set up our base case. That's the if n equals 1. This is our stop sign. It's what prevents an endless loop. If we haven't hit that base case yet, the function does something incredible. It calls itself with a slightly smaller number. Return n times factorial n minus 1. And that right there, that's the recursive call. So what this does is it creates this incredible chain reaction. Our first call to factorial of 5 doesn't give us an answer right away. No, instead it pauses and it calls factorial of 4. And that call pauses and calls factorial of 3. And this goes all the way down until factorial of 1 finally hits our base case and just returns 1. Then the answers start multiplying their way back up the chain until we get our final answer of 120. Here's a good analogy. It's kind of like tackling a huge task by just repeatedly solving a smaller, identical version of that same task. You just keep breaking the problem down and down and down until it becomes so simple you can solve it instantly. And then you build the full solution back up from all those tiny, simple answers. And just like with our while loops, recursion absolutely positively needs an exit condition. We call this the base case. In our factorial example, it was that if n equals 1 check. If you forget that, the function will just call itself forever. Factorial of 0, factorial of -1, on, until your program completely runs out of memory and crashes. So remember, always define your exit condition first. Okay, now we've reached the climax of our journey. Let's explore the two very different ways that functions handle data. And I'm not exaggerating when I say that understanding this gets to the very heart of how C manages memory. This is one of the most critical concepts for any C programmer to master, period. So when you send data to a function in C, it can happen in one of two ways. For simple things like integers or characters, C sends a copy of the data. We call this pass-by value. But for bigger things, like arrays, C does something different. It sends a map to the original data's location in memory, and that's called pass-by reference. Let's use a little toy car analogy to see exactly what this means. First up, let's talk about pass-by value. Imagine you have a little toy car. When you pass that car to a function, you're not actually giving it your car. You're giving it a perfect photocopy of it. Now, the function can do whatever it wants to that photocopy. It can paint it, it can take it apart, but your original toy car, it's safe and sound, totally unchanged. So in this piece of code, we have a function called changeValue, and its whole job is to take whatever number it gets and change it to 100. Back in our main program, we'll create a variable called mynum and set it to 5. We'll print it, then call the function, and then we'll print it again to see if anything actually changed.
And just look at the output. Before we call the function, mynum was 5. And after the call, it's still 5. See, even though the function changed its own internal copy, which was named x, our original variable back in main was completely unaffected. Why? Because it only ever got a copy. But arrays are totally different. They are always passed by reference. So now, imagine you don't just have one toy car, you have a whole toy box. That's your array. Instead of trying to copy that entire heavy box, you just give the function a map, a set of directions to your real toy box. Any change the function makes now, well, that change is permanent. Okay, so this function, changeArray, is built to do one thing: modify the very first element of any array it receives. So back in main, we'll create an array called myArray. We'll print out its first element, then we'll call the function, and then print that first element out one more time.
Can you see the difference? I mean, look at this output. Before the call, the first element was 1. After the call, the first element is now 100. Because the function received a map, which is really the memory address, to the original array, the change it made, it stuck. It modified the actual original data. Okay, this is a huge be careful moment in C programming. This behavior is incredibly powerful, for sure, but it can also be really dangerous. An accidental change you make to an array inside a function isn't isolated. It's a real permanent change to your data that can cause these really subtle and incredibly hard to find bugs later on. So why does he even do this? Well, it all comes down to one thing: efficiency. An integer is tiny, making a copy is fast and cheap. But an array could have thousands, even millions of elements. Can you imagine copying a massive array every single time you pass it to a function? It would be incredibly slow and would waste a ton of memory. So C takes the smart, efficient route. It just passes the address, that tiny little map, which is super fast. So let's put it all together in one final summary. For a simple type like an int, you're sending a copy of the toy. Any changes made inside the function, they do not stick. But for a big, complex type like an array, you send a map to the real toy box. And the changes, oh yeah, they absolutely do stick, and your original data is permanently modified. And honestly, understanding this fundamental difference between passing by value and passing by reference, it's so much more than just a rule you have to memorize. It's a core concept that really empowers you to design and write safer, more efficient, and way more powerful C code. It forces you to actually think about where your data lives in memory and who should be allowed to change it. Thanks so much for watching.